Okay, supervised learning. So I'm going to give you, it said intro to machine learning. It's going to be just really an introduction to the data set we're going to be playing with, because I think we've covered introduction to machine learning, and then we're going to look at models, evaluations, and ensembles. And we're going to do it for real, though. So for this use case that we're going to be playing with at first, I want to imagine that you're looking to buy a house. I don't know, is that something you do here? Some places they don't, right? I mean, they're just like, the big city and they just all rent. But where I live, you buy a house because all the rentals are taken up by the students. Okay, and you've recently found a house you like. It's not haunted, so that's good. Okay, and you just want to answer the question: is the asking price fair? That's what you want to know. Okay, are they asking too much or too little, or is it fair? Okay, so what next? So traditionally, you might ask an expert, right? A real estate agent. You go to the real estate agent and you say, "I like this house. Is the price fair?" And of course, as Charlie was covering earlier, the problem is that these experts can be rare or expensive. Now, agents aren't that rare, but they certainly can be expensive. More importantly, however, it's really hard to validate their experience, right? The agent you're talking to, do they have an experience with similar properties? Do they know anything about houses that aren't haunted? I don't know. Do they consider all of the relevant variables? Are they actually looking at the market and thinking about everything that could be impacting the price? Is their knowledge of the market up to date? Or they just took 10 years off and they suddenly came back to selling homes, right? So they really have no idea anymore. Even worse, it's hard to validate their answer. They say, yeah, that price is fair. And you say, okay, tell me why. How many times have they been right or wrong in the past, right? They gave advice to 10 other people and they were wrong every time. And they probably can't explain their decision in detail. Oh yeah, and humans aren't really very good at statistics, intuitive statistics, okay? So let's replace the expert with data. So we'll start with an intuition, which is that the square footage should somehow relate to the price, right? That seems pretty strong. And we'll collect data from all the past sales. So we'll look at every home that's been sold in the last 6 months or a year or whatever. And we'll build a table of square footage and how much it sold for. Okay, this is actual data from the Corvallis market, by the way. Okay, and now we'll just plot that. So there you go. So that's square footage there on the X and the price on the Y, and you get this kind of splattering of prices on there, okay? And we'll just draw a line through it, which may be something you did in a math class at one time, maybe not, I don't know. But you could imagine drawing a line through there, and we would call this a linear fit. Okay, so it's just an equation that looks something like some number, all right, times the square footage plus some base price. So apparently homes in Corvallis are worth almost $100,000 even if they have no square footage, which actually sounds about right, if I'm honest. Okay, and so then you get, those are the predictions. So you take that model and you run the square footage through and you can see how those predictions compare to the actual sale price. So this model's not terrible, right? The actual 360 and this model will predict 400 and 307, 320. It's not too bad. Okay, so how did we do on replacing the expert? That's what I want to ask. Okay, this is not a rare or expensive thing to do. It's pretty easy. All right, I didn't tell you, but the data is very easy to get. The website I use, you just click on the filter and there's a button that says gives me a CSV. You have a CSV, so it's very easy. We know that there's similar properties. Okay, it's very easy to validate that the house I'm looking at has a similar square footage. Okay, so I know that this data is relevant. I just pulled the data, so I know the market information is up to date, right? This model is very up to date. If it isn't, I can update it again. 6 months from now, I can build another model, no problem. I can actually show you exactly how many times that model has been right or wrong. That's easy. And I can explain the decision in detail. It's related to the square footage. It's a linear model. Very simple. Okay, we did kind of fall down there though, right? We just looked at square footage. And we still used an intuition. Okay, we started with an intuition that the square footage relates to price. And we only use the square footage. So that's okay, we'll just use more data. Okay, we'll just use it all. And actually we're gonna use one that has even more data than this because I couldn't draw it. But so you got square footage, the number of bedrooms, the bathrooms, maybe the address, where in the town, the latitude, the longitude, so now what? So can we still fit a line to these 10 variables? Well, yeah, actually you can. Will it give good results? Probably not. Okay, it worked pretty badly. And what about those text fields and categorical values? Okay, so the one field that isn't on this one that we're going to use actually has the full description of the house. You know, like when you write the ad, you say, this charming 3-bedroom home on a cul-de-sac is, you know, wonderful for kids. We're going to use that too, right? So what are you going to do with that stuff? And of course, this is where we're going to hit it with machine learning, right? Okay. So we're imagining some kind of a mythical machine learning model. We want it to have high representational power. We want it to somehow magically understand these home prices. So fitting a line is an example of low. A deep neural network is an example of high. This is kind of like that slide I was showing you before. You have complex data, maybe use a neural network. You have simple data, maybe use a linear model. We want something that's easy to use, easy to configure, easy to interpret. How was this decision made? Easy to put into production. We want to work with real-world data, mixed data types, numeric, categorical, text fields. It's got to do all this. It needs to be able to handle missing values. This data set is rife with them. Okay, there's houses that have no bedrooms and houses that have no bathrooms because the values are just missing. It needs to be resilient to outliers. There's a few outliers in this data set too, really bizarro. Giant mansions in Corvallis. I think there's one with 9 bedrooms or something insane. Okay, and there's actually hundreds of possible choices, but the one we're going to do first is a decision tree. So you remember this from Charlie's presentation. This is an old version of a slide I pulled off of his, so it doesn't look as nice. You've updated, they look much better. But we're building a model by making these decisions, these splits, right? Segmenting the data on these rules until we have sort of this pure rule set that gives us the information we want. So this is actually what we're going to do. So let's do it. Okay, so here is our BigML UI, and actually let me go full screen. And I know that you've seen a little bit of this. Let me see if I can not drop my laptop. Okay. Is that big enough? No, it's too big. Still, maybe that works. Okay. It's bigger on my screen, that's why I'm a little. Okay. So I'm going to do a direct upload, and I'll show you what this data looks like. Okay. So we have the address, we have the zip code, we have the number of bedrooms and bathrooms, we have the location. You'll notice that just by uploading the file, it's already auto-typed all the fields, right? So it assumed the address was a text field, okay, which is probably okay. And the zip code is a numeric, and the location is a categorical, because there's only a certain number of locations, like Country Estates and Tamarack Village. We have the square footage, the lot size, the year built, parking spots. And we even have this remark fields, which is, Timber Hill, Charmer, well-maintained, 4-bedroom, 3-bath on a quiet cul-de-sac. Okay, so that text. You notice that it says that's a categorical. So I'm going to fix that. So this is why we have the source step, is because the auto-typing isn't always perfect. And in this case, the data set is small, and so it doesn't have quite enough information to recognize that as a text field. It thinks that there's only a few distinct items, and so that must just be a list. But we can fix it, no problem. So we can actually change any of these field types. Okay, so I can just come down here and say, no, remarks really should be a text. Okay, and if you so chose, you could actually come in here and dial up the text settings. So I could say, no, don't auto-detect the language. This is supposed to be Korean. All right, I could do that. I can decide whether or not I want to do this tokenization process for me. I can also do n-grams. You guys familiar with n-grams? Yeah, okay, a few people? No? So the idea is rather than just look at individual tokens, you actually look at the frequency of tokens occurring together. All right, so the example that always pops into my mind for some reason is a vice president, right? You want those two together. That means something different than vice and president separately. So you have to look at the association of words nearby. Yeah? So you can do that up to 5 grams, so you're looking at blocks of 5 words. Okay, so we'll just leave that though. Okay, so numeric, categorical, and text fields. No problem. That's the last time we're going to think about it for right now. Okay, everything else is just going to work more or less transparently. So with the field types correct, we're going to go ahead and create a data set. Okay, and now we can see some of the summary statistics. All right, so we can see that there were 3 zip codes in this data set. This house here, oh, sorry, it's 6 bedrooms. So there's 3 houses that have 6 bedrooms. Most of them have somewhere around 3 to 4, for example, and bathrooms. There's 59 with 1, and look at this one here. There's 1 house with 5 bathrooms. That's like 1 for everybody. Yeah, I don't know. This, okay, and for the text fields, you get these nice tag clouds, so you can see what kinds of words people are using to describe their homes for sale. Okay, lots of people have done some kind of updated. People really like talking about their kitchens, apparently. That's a really dominant word that people use. to describe their house. Probably it has a new kitchen or updated kitchen, would be my guess. Okay, but we're not going to worry about any of that. We're just going to go ahead and build a model. So let's configure a model. The only thing we're going to do is tell it what to predict. Okay? I should slow down a little bit there. So you can do a one-click model, and it'll just take the default settings and predict the last column in the data set. Okay? In this case, that doesn't work because the last column in the data set is the longitude. And although it'd be interesting to build a model that predicts where it is physically in one dimension of the Earth's surface, it's probably not a very relevant model. So we wanted to predict this last sale price. Remember, that was the thing we were trying to do, predict home prices, right? So instead of doing the one click, I'm going to do a configure model. And this is where you have settings. So there's advanced settings. Okay, you could play around in here too. We'll play around there a little bit. But I'm just going to tell it the objective. So I want it to predict the last sale price. Okay. And with that, we'll go ahead and let it create the model. And so now what it's doing is it's looking at the variables that affect the home price and trying to find the one that is the most dominant for segmenting the value of homes. And that goes at the root of this tree. And that indeed is the square footage. So our intuition is matched by data in this case. Okay, and you end up with these branches, which as I hover over, you can see on the right-hand side there, it's showing us what that split value is. This is homes with a square footage of greater than 2,000. Okay, and you can see a predicted value of just close to 500,000, and there's some expected error there, all right, which is the range at which it thinks that price sits, okay? And you can see how much training data there is. About a third of the homes go through here. And as we go down, we're adding more splits. And so I can actually zoom in here, and we can look at this one. So here we have a home that's greater than 2,000 square feet, additionally greater than 3,800 square feet. The remarks contains the word bath, and the remarks also contain the word shopping. And then we have, this model's predicting this home is going to be close to $1 million. And that actually makes pretty good sense for the Corvallis market because that is a ginormous house, and all of the ginormous houses are way outside of the downtown area, which would not be anything to do with shopping unless they write in the remarks, you know, fantastic home, super far from shopping. Okay, you can do a little bit better with this model with doing some topic modeling and stuff, and then you can see those patterns in the text a little better, but it's okay for this for right now. Okay, so let's use this model to make a prediction. That was the thing we want to do, so we'll put our home in. So I can come down to this menu here, and I can say, just make me a prediction, and it's going to give me a form, all right, where I can input new data, and it will tell me the predicted price. So I can say, okay, my home is that I'm looking at is just under 2,000 square feet. It's charming, I guess, and we'll give it, I don't know, a medium-sized lot or something. Okay, and there's my predicted price up at the top there. All right, so you can just input new data now and get a prediction for what the home value will be in the Corvallis market, where we've trained this. Not for your market, probably. Okay, so that was that whole life cycle, source, data set, model, prediction. Okay. All right, so just to make sure what just happened, we started with this housing data as a CSV, okay, from this company called Redfin. We uploaded it to create a source. I fixed the source because one of the field types was wrong. Then we created a data set and reviewed some of those summary statistics. We didn't one-click. That's a lie. This slide is a lie. And then we predict the home prices based on the housing features. We explored that model a little bit. I kind of showed you around the tree a little bit. Not a lot, but that's okay. We used it to make a prediction. Okay. And we can come back and I can show you a few more things in the tree visualization. But I want to talk first about why you want to use decision trees. Okay? So they work great for classification and regression. Which kind of problem was this, by the way? It's a test. Regression, fantastic, right. It's super easy to remember regressions. You're predicting some kind of a numeric outcome. Home prices, numeric regression, okay. If we'd been predicting, is this house a good deal, true or false, that would be a classification. So anyways, the decision trees work for either one. It doesn't care. It doesn't, you just tell it this is a numeric value and it goes, okay. You tell it this is a categorical value, okay, no problem. It's really easy to understand that model, right? The splits are features and values. I can tell you exactly how this thing is making its predictions. I can look at any branch in this model and tell you precisely how it's making its prediction, right? We can look at this one right here, and it's deciding that that's the predicted value because those are the bounds in the square footage, the lot size, the year it was built, and as I go further down, words that were considered in the remarks. I can tell you exactly. It's very easy to introspect. It's lightweight and super fast at prediction time. Okay, it's also actually super fast at training time. I should put that in there. But the idea is, when you're making a prediction, really all it's doing is it just looks at the root of the tree. You give it some input data, and it looks there and goes, okay, that's question 1, that's question 2. Hey, there's your prediction. So it's just a series of questions that it compares to the data you give it, and then it gives you an answer. So you can imagine this is like a big if then else, right? And computers are really good at branching. Okay, super fast. It's relatively parameter free. I didn't really configure anything. Okay, your data can be messy. Useless features are basically ignored for you, all right? Because it's looking for features and values that segment those houses, and if there's one that doesn't do anything, it goes, meh, I don't want that one. Okay, it's parsimonious. It works with unnormalized data. You don't have to have all your data beautifully normalized and everything. House prices and number of bedrooms are totally different scale. The decision tree doesn't bother, no problem. That's not true for all algorithms. It is true in BigML because we do the normalization for you when it's important. Okay, but normally you would care about this. It works with missing data. You could have missing data in there, also no problem. So at training time, so imagine this is a loan. I should stay with houses, but that's okay. And maybe you don't want to tell me why you want this loan. That's one of the questions. Why do you want this loan, right? And I want to buy a car, or I want to pay off credit cards. And for some reason, your loan application it says, why do you want this loan? You were like, I'm not telling you. Or you left it blank. That's no problem. The tree can still handle those missing values at training. You can even make that a split. You can say, no, Mr. Decision Tree, consider missing values as new data. Make a rule about if they don't tell you why they want this loan, that's something you should learn from. Okay? And it works with missing data at prediction time, too. So normally, you would just do question 1, that one's missing, you would stop. How do you go further if there's no answer to that question? Right? So that's one way. You can just have the decision tree do that. You can say, that's your best guess, because you don't know anything. You don't know the next question. But you can also just say, well, if you don't know that one, just skip it. And just ask both of those. Okay, and keep going until those paths terminate. And then just average those 2 results. It's going to be somewhere in that range. And so that works really nice, too. But it's sort of built in. You have this way of handling missing values at prediction time. It's really quite resilient to outliers as well. And it has a high representational power. Take my word for it. Okay. And works really easily with mixed data types too, right? Numeric, categorical, date times, text fields, even items. It just, off you go. Okay. Now that I've sold you on decision trees, let me tell you why you don't want to use them. It's slightly prone to overfitting. Remember this thing? It's slightly prone to overfitting. Maybe you don't always like decision trees. Okay, we have some ways of combating the overfitting. There's some statistical tests to make sure you prune the nodes. But basically, it might overfit a little. And we can also fix this with ensembles, which we're going to do. Yep, if I move faster. Okay, the splitting prefers these decision boundaries that are parallel to feature axes. I'm just going to kind of explain that with a picture. So imagine this is my data. You can see there's some kind of a diagonal pattern, right? You can see that? I want to separate green dots from red dots. I want a model that separates those. That line does a really good job. So if I could just tell you a split that's diagonal, I'd be done. One split, boom. But decision trees can't do that. Okay, not unless you transform the data. Okay, because it can't split on 2 variables at the same time. So instead, it's going to do something like this. It'll split that way, and then it'll split that way, and then maybe it'll look at that gray box and split again and split again. Okay, it's just going to keep splitting until it ultimately finds all these little chunks that represents that same diagonal edge. Okay, that's okay, but it's not always ideal. Okay? You just give it more data. If you give it enough data, that problem is fine. It'll find those more complicated decision boundaries if you have enough data. Very small data set, it could be a problem. So predictions that are outside your training data can be a little problematic. So if I gave you this decision tree, right, this space is split, there's all those splits, and then I asked you what's the value of that black dot there, okay, it's really hard to say because in that region there's 1 red and 1 green, all right, but if we think again about the line, it's a little easier to see what it might be, right? Of course, the idea there is that we're forcing a distinction on how this data should be structured. We're saying it should be split in a line, and then it's obvious. This is just a nuance of how you're modeling, okay? But in this case, predictions with outliers can be a bit problematic. You can catch this with model competence using an anomaly detector. Okay, it can be sensitive to small changes in training data. This one could be a little bit more annoying. So here is a bunch of splits. Let's add 1 data point, and let's split it again. Okay, By having that one data more red dot there, maybe the first split ends up being up there instead. Okay, so remember last time the first split was down here. I had one training data and I retrained the tree and suddenly it's splitting on a totally different thing. That's the very first split. So the very root of the tree, you had just a little bit of training data and suddenly the root is some other variable or some other value. That can be a bit concerning, right? If you care. Sometimes you don't care. You're like, whatever, if it works, fantastic. But sometimes you care, okay? So what other models can we try? And how will we know which one works best? That's the question. Well, we're going to do an evaluation, of course. This should be easy, right? So this is our churn data again. We could just build a model. We can just take all that data, run it through the model, and we can just count up all the mistakes. That said that customer actually did churn, and the model says no, so that was a mistake. I'll just count them up. That's easy. But remember this. Right, it's a little more nuanced than that. We want more than just a count of mistakes. We need a way to separate what kinds of mistakes we're making. Okay, in the churn example, it might be that mistaking that a customer churned when they didn't is a different cost than predicting that a customer won't churn and they do. Okay, we need a way to separate those two different kinds of mistakes. All right? So we need better metrics. So this is where it's going to get a little heady. Stay with me. But I believe fully in explaining these evaluation metrics a little more rigorously than we've done in the past. So here we go. So I want you to imagine we have a model that can predict a person's dominant hand, okay? That is, maybe you show it a picture or you give it some profile. You know, they say they really enjoy music and mathematics, and you go, oh, that's a left-handed person. Whatever it is. But somehow it takes this information about a person and it tells you whether or not their dominant hand is left or right, okay? And we're going to define the positive class. That's something you're going to hear a lot. What's your positive class? It's arbitrary. It's just whatever you're really interested in. I like to think of the positive class as the thing you care about right now. That's my positive class. It's the class you're interested in. The negative class is the other one, okay? Or the others, if there's a bunch. So maybe you have 10 classes. The positive class is the one you care about, and 9 are the negative. Okay, so for this example, our positive class is going to be left-handed, because I'm left-handed, so that's why. Okay? So we choose the positive class is left. So we're going to define something called a true positive. What does this mean? So we predict left, and the correct answer was left. The model looked at somebody, it said, that person's left-handed, and they actually are true positive. Okay, true negative, we predict right, and the correct answer was right. Remember, negative means it's the negative class, so we got it right. Okay? Okay? False positive, this is why I did left and right. False positive, we predict left, but the correct answer was right. So we made a mistake, okay? But we made a very specific mistake. We made a mistake in the positive class. We predicted left, and it wasn't. And then you can imagine then a false negative is we predict right, but the correct answer was left. Okay, we predicted the negative class, right-handed, but they were in fact left-handed. So we gave a false negative. Okay, if that doesn't make it simple enough, remember, true positive, underlined. True means you did something correctly. Okay, whatever it is. And positive means you did the positive class correctly, whatever it was. All right, true negative means you correctly predicted the negative class. True, correct, negative, negative. False means you did something wrong. Okay, so false positive means you incorrectly predicted the positive class, and a false negative means you incorrectly predicted the negative class. I made this slide for me as much as for you. I forget all the time too. Okay, now we can start thinking about some metrics. Okay, and you don't have to worry too much about the formula. It's mostly just there in case you're formula inclined. I am. I always think of these metrics in the formula for some reason. But this is, you take the true positives plus the true negatives, so it's basically the count of all the things you got right? All the things, the positive class you got correct and the negative class you got correct. It's everything you got correct. And you divide it by the total number of things. So it's the percentage. It's like when you're in college and you took an exam and you got a 71. That's the accuracy. All right, if the accuracy is 1, you made no mistakes. Everything's perfect. If the accuracy is 0, then everything was a mistake. It's all wrong. Okay, in which case you could just flip the model around, but that's okay. So accuracy is intuitive, but not always useful. It's a bit of a hedgy one. Accuracy is like the first, oh, that's really accurate, but then maybe accuracy is what you care about, and I'll explain that. In particular, you have to watch out for unbalanced classes. Okay, so this is the other reason I chose this model. 90% of people are right-handed and 10% are left, according to some random web page that I Googled, just like you would. And you could just build a model that just always says everybody's right-handed. Right? It doesn't do anything at all. All it ever says is right-handed, right-handed, right-handed. Okay, and that model would be 90% accurate. No problem. So, I mean, this is fantastic accuracy, but arguably useless, okay? Now, a better example of that might be to think about fraud, right, where you also have unbalanced classes. We have very few examples of fraud, and you have lots and lots of examples of not fraud. So you can build a model that just says every single transaction is totally fine. Yeah, let that go through, no problem. Okay, and you're gonna be right like 99% of the time, maybe higher. Okay, but the problem is that little 1% where you're wrong are the ones you actually care about. Okay, they're the super most important. Okay, so pictorially, and I forgot my laser pointer, that's all right. So we have the positive class, okay, and the negative class. So remember, the positive class are the people that we classify as left-handed, and the negative class are right-handed. And the red and blue dots are what those people actually are. So imagine this like a sorting. We're putting people into boxes. So this model put everybody into the negative class, including those 3 left-handed people. Okay, so this model put everybody into the right-handed. It said everybody was right-handed. Everybody sees that? Okay. Yes? Oh, thank you. How does it work? Ah, yes. Okay, so our true positives are going to be 0. Okay, because we didn't predict anything in the positive class, and we didn't get any of them right. Okay, so that's 0. And the false positives is also 0, okay, because we got all of the false positives. Okay, and the true negatives is 7. Here are 7 people that we predicted in this class, in the negative class, that are correct. Okay, so the true negatives is 7. And the false negatives, that's these 3 ones right here. We predicted the negative class, but we got them wrong. Remember, false means we got it wrong, and negative is what we got wrong is the negative class. So that's 1, 2, 3. And so the accuracy of this model is 70%. Yeah? Okay, we have to dig a little deeper. So hopefully that worked. Everybody's good? Are you confused or bored? Because I can go faster. No? It's good? Good speed? Okay. All right, so let's talk about precision. Okay, so now it's a little different metric. Now we're looking at the true positives, and we're dividing it by the true positives plus the false positives. So if you think about that, we're only thinking about one class. We're only thinking about the positive class. That's it. We're not thinking about the negative class anymore at all. So you can think of this as the accuracy or the purity of the positive class. Remember, the positive class is the one you're interested in right now. Okay? So it's how well you did separating the positive class from the negative class. That's what this metric is telling you. If the precision is 1, then you made no false positives. Do you see that? Okay. You may have missed some left-handers. Okay, you may have missed a few of them, but of the ones you identified, all are left-handed. So whenever the model said you're left-handed, it was always right. A few left-handed people might have gotten through that it thought were right-handed, but every time it said you're left-handed, it was right every time. Okay? That's the difference of precision than accuracy. If precision is 0, then there's no true positives, meaning that none of the left-handers you identified are actually left-handed. Every time the model said you're left-handed, it was wrong. Every single time. You're left-handed. Oh, I'm not. It was wrong. That would be a precision of 0. So again, it's telling the accuracy of that positive class, just the one class. Okay, so we'll move the dots around a little bit. Here are the people we predict in the positive class. Here are the people we predict in the negative class. And so you can see our true positives are 2. Okay, so remember our positive class is left-handed. We have 2 people that are left-handed, correctly identified. And our false positives is 2. We got these ones wrong in the positive class. It's 2. And our true negatives is 5. Okay, these are the ones that we got correct in the negative class. And our false negatives is 1. One left-handed person escaped. Okay, one left-handed person got stuck down here and the model said, you're right-handed. And they went, not, come on. Build a better model. And the truth is we don't care about the negative class for precision. That's the idea. So now you can just ignore the lower part of that picture. And the precision is only interested in this. In which case the precision is 50%. It's the accuracy of just this one class. Right? Cool. Now we can talk about recall. So recall goes hand in hand with precision. Okay? This is the percentage of the positive class correctly identified. So now we're interested in how much of the positive class we actually got right. Okay? So it's a measure of how well you identified all of the positive class examples. I read this great analogy, something about fish swimming and you're catching with a net. It's like how many go by or something. But I don't own that analogy, so I can't ever explain it right. But if that works for you, then think about fish. Okay, sorry. Okay, if the recall is 1, then there's no false negatives. Right, you see that? If this is 1, there can't be any false negatives here. This have to be equal for that ratio to be 1. And so all the left-handers were identified. So you imagine the set of all the people that the model tested for being left-handed, and all the people that identified as left-handed, it found them all. Okay, they were all in there. None got away. No fish got by the net. Okay? There may be false positives, so the precision could still be less than 1, though. You may have still made some mistakes, but you got them all. If the recall is 0, then there's no true positives. The only way this ratio can be 0 is if that's 0 up there. And so there's no left-handers identified. You missed them all. You put your net in the water and every single fish went by. You didn't catch a single one. Okay? I guess I did make the fish analogy work. Okay, so again, our same setup here, and our true positives, that hasn't changed. But now we're just looking, so if you just gray this out, because again, we're only interested in the positive class. So the difference between precision and recall is that precision, we were looking at how well we did just in this one class, and now in this, predicting this class, and now we're looking at how well we did for this class, essentially. So we made 2 right and 1 mistake, and so our recall is 66%, 2/3. We found 2/3 of the left-handed people correctly. That's what recall is telling you. Okay, so if you have recall of 100%, that means you found all the left-handed people. If you are building a model that predicts fraud and you have recall of 100%, you found all the fraudsters. Okay, you might make a whole ton of mistakes in that model, claiming lots of people are fraudsters when they aren't. All right, lots of mistakes, but you found all the fraudsters. That's the difference. Okay, now don't worry too much about this one. I don't want to give everybody a mathematic conniption, okay? But there's something called an F measure. And because you have this problem where sometimes it's like precision and recall, and I'm not really sure. I kind of care about them both. And if you care about them both, then you're going to use this measure or the next one I'm going to show you. And so it's at least nice to know what it means. So this is the harmonic mean of recall and precision, okay? If the F measure is 1, then the recall is exactly the same as the precision, and they're both 1. Okay, so if you have a high F measure, then both your recall and your precision are high. That's what that means, okay? If the precision or the recall is small, then the F measure is small. So if you did poorly on either recall or precision, it pulls the F measure down. So the F measure gives you one nice measure that tells you how well you did on both precision and recall. Does that make sense? Okay, if it's high, you did great on both. If you did poorly on either one, the F measure will be low. And you can also do something called the phi coefficient, or phi. And this is going to give you a value between -1 and 1. So if it happens to be -1, then the predictions are opposite reality. So you can just stare right at that equation, and that's obvious. No, it isn't. If it's equal to 0, then there's no correlation between the predictions and reality. This model is just guessing, essentially. And if it's 1, then the predictions are basically always correct. So it's just another measure you can use. If you care about all of these classes together, then you would typically be looking for a model that's as close to 1 as you can get. All right? Okay. Okay. So let's do an evaluation. That was enough talking about evaluations. So I'm going to use a different data set for this. And actually for this one, I'm going to throw caution to the wind and try to do this from Dropbox. So I have this set up in my Dropbox account, and it is in here. Sweet. So you can also connect this to various cloud storages. You can pull data files directly in that way as well. And so this is actually a very famous data set. It's available in the UCI repository. It's a study of female Pima Indians in the United States, looking at their diagnostic measurements. You have things like the number of times they were pregnant, their 2-hour plasma glucose, their blood pressure, and things like that. And then down here you have this categorical, which is, do they have diabetes or not? True or false? And what we can do with this data, there's lots of things we can do with this actually. It's a pretty fun data set. Is we can build a model that predicts if you have diabetes, right? We can just tell the model, take that data and predict diabetes for me. And then you could just plug in your 2-hour plasma glucose and your BMI and stuff, and it'll say, yep, you got diabetes. Okay, it might make mistakes, but the model is going to do it. So we'll just one-click our way through this. Actually, I could do this with one click, but I'll do it in 2 one-clicks. Okay, so I'm just going to do a one-click model. So here's our model that predicts diabetes. Okay, And at the root, we get the plasma glucose. And what do I want to show you anything else about this one? I didn't spend a lot of time on this tree visualization, and I got to speed up just a touch. But there is also this PDP thing. It's a good time to introduce this. You saw a picture of this in the talk I did earlier, but this is a partial dependence plot, and you're basically looking at a decision boundary in 2 dimensions. Okay, so on the x-axis there, we have the plasma glucose, and on the y-axis, we have the BMI. And what this is, the decision boundary just on those 2 variables, showing which of these patients the model predicts has diabetes. This blue area is false. You can see upper right-hand side there. And this orange area is true, okay, with a high confidence. And this area is still true, but with a lower confidence. And down here, same kind of thing. It's true, but low confidence. All right, so you can see visually how the decision's being made in 2 variables. And you can change the variables. So instead of plasma glucose, I could put, tricep skin thickness or something. And you can also see how other variables are affected as well. If I wanted to see how the number of times you were pregnant impacts this, I can change that variable down there as well. Okay, well, let's evaluate this model. Let's do an evaluation. So to do an evaluation, remember we need to pass it a data set. So we'll just run it through the same data set again. We're going to do an evaluation. And now it's going to compute all those metrics that I was talking about, okay, and it's going to show them to us, all right? And so here we go. Here we have our accuracy, our precision and recall, our F measure, and our phi coefficient. Okay, we have what's called a confusion matrix there because it's simple to understand. That was a joke. Okay, but the number of times we predicted false, and it actually was false, 499 times. And so you can see the recall there of 99%. And here, true, and it was true, is 268, so recall is 100%. So this model is fantastic. We're making medical science here. We've just predicted diabetes like nobody, right? That's pretty awesome. Hold that thought. Okay, just to review, we started with the source. We created a data set and then a model. Using the model and the data set, we created an evaluation. We reviewed some of those metrics. Okay, I showed you very briefly anyways. The confusion matrix, I showed you the accuracy, precision, F measure, and phi. And you'll notice the phi is also very high as well, 0.9, F measure 0.999. Fantastic. It seemed to perform really, really well. So can we trust this model? No. No, this is a great time to talk about the evaluation danger zone, which always makes me think of that ridiculous movie. You know the song. Yeah, thank you. Perfect. Highway to the... Okay, never evaluate with your training data. That's what I just did. Okay, so many models are able, and decision trees in particular, are able to memorize the training data. They basically just remember what the rules were. Okay, so this will result in overly optimistic evaluations. So what do I mean? So here's our training set. Here's our evaluation set. Those values in both data sets are exactly the same. So the model knows that if those are the values of your diagnostic measurements that you have diabetes, and so when you ask it, hey, if I give you the data you already saw and that patient was true, what do you think? The model's going to go, that's true, come on, it's so obvious. What's wrong with you? So who needs a model, right? You could just pull the patients out of there and say, yeah, guess what, you have diabetes. What we want to know is how this model performs on values never were seen at training time. I want to take a pool of patients, build this model, and a new patient comes in that I don't actually know, and I need to know how well this model is going to do. Very important. Okay? I want to know something like that. That's not in the training set. Okay. So if you only have one data set, you're going to do something called a training and test split. All right? So we're going to take our original data that we have, and we're going to split it. We're just going to take some of the patients out, hide them. And we're going to train the model just on the left-hand side, and then we're going to ask the model to predict the right-hand side, and we know the answers to the right-hand side, so we can see exactly how, or we can at least see our interpretation of how the model is going to perform on data that it didn't see at training time. Okay? So this gives us a better evaluation of how the model will perform with new data. Sometimes this isn't enough. You might just get lucky. That actually can happen with this diabetes training set. There's some anomalies in there, and depending on whether the anomalies go in the training set or the test set, you can get wildly different evaluations. So the solution there is to repeat several times. You can formally do something called cross-validation. If you're interested in that, think about it. Otherwise, go ahead and ignore that statement. And let me show you how this changes. Okay, so we're going to go back to our data set. And instead of just doing the one-click model and then evaluate it, this time I'm going to do a training and test split. So here we have different ways we can transform a data set. We can, I I didn't mention this, but data sets are fundamental building blocks. So data sets can become models or clusters or anomaly detectors. They can also become new data sets. So you can transform a data set, you can add features, you can aggregate them and join them and do some database-y type things you might think of doing with a data set. And one thing in particular we can do is a training and test split. Okay, so in this case, we'll just take the defaults of an 80-20, and actually I'm going to use a seed as well, so I get the same results every time. And now, because, as Charlie mentioned earlier, these are immutable, you'll notice that I have two new data sets. Okay, so I have my original data set, and I have a new test set and a new training set. So this one has 80%, and this one has 20%. So 20% of our patients have been held out. So I can just, right from here, I can do a one-click model on that. Okay, that's going to start it up in the background. So I'm just building a model on 80%, and now we'll evaluate on the other 20%. Excuse me. And you'll notice that it knows that we built a test set, so it goes ahead and puts that in for me. Hey, you probably want to evaluate with that. Okay. And let's see how we do. Okay, this is a slightly more realistic example. Okay, this is much lower, right? Okay, the accuracy is only 73%. The F measure, it's not too bad, but it's 7, 8. The phi coefficient is, much lower. Okay, much more accurate representation of how well this model is actually doing. Okay, so watch out for that. Now, maybe you thought about this. When it says that the precision is 80%, which class is it thinking about? Remember, that precision is computed for one positive class. And is it true or false? That's the two classes for diabetes. Which one is the positive class in this situation? It's false. It's right here. So you have to set it. So if I want to see what the precision is for true, then I can just change it here. And now those metrics are all for the true class. So remember, the decision of what is the positive class has nothing to do with whether or not the class is true or false. It's whichever one you're looking at. And I know that terminology is horrible, but these metrics are showing you for the class that's highlighted there. It is worth also looking at something called an ROC curve here, which actually shows you the false positive rate versus the true positive rate. Oh, I gotta speed up a bit. In particular, there's something here called the probability threshold. So the default threshold, okay, in a model for probability is 50%, as you might expect. If it says you have diabetes with 51% probability, okay, then it says you have diabetes. If it says you have diabetes with 49% probability, then guess what? Predicting you don't have diabetes is 51%, so it tells you that. Okay, but you can change that threshold. You can move it around. You can say, no, 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 don't tell people they have diabetes unless you are 90% sure. Okay, don't say diabetes is true unless you're 90% probability. That's going to change how these metrics look. In particular, it's going to change if you look at the confusion matrix. As I move this threshold around up here, the slider, you can see how it's changing the counts, right? So if I move this probability threshold up, you can see I can get the recall on false as high as I like. Okay? I'm allowing more and more mistakes so that I optimize one class. Or I can go the other way and say, no, just tell everybody that they have diabetes, okay? Just tell everybody, you have diabetes, okay? Even if 0% probability, then my recall on true is 100%. I got them all. I made a whole bunch of mistakes, but I found everybody has diabetes. Okay, but the game here is that you can now slide this up a little bit and decide how many mistakes you want to make. Okay, I'm willing to get a 90% recall on true, or I'm willing to get an 85% recall. I want to choose that operating threshold for the number of mistakes I'm willing to trade off. Okay, which is a cost benefit. So this is a business side. You have to decide what's valuable to you. Okay. So starting with the diabetes data set, we did the training test, we built a model. The scores were much worse. Then we launched several other types of models, which we didn't do yet. That slide's also a lie. Stay tuned. Okay. Let's come back to the danger zone. Don't forget that accuracy can be misleading, right? It's mostly useless with unbalanced classes. You can use something called weighting and operating points, or you can use the OptiML. That'll also do stuff for you too. I did mention the operating points. Let me explain that one more time. So the default probability threshold is 50%. Changing the threshold can change the outcome for a specific class. And so here you can imagine we've got some loan information. So here's the interest rate and the monthly payment and what actually happened, right? This loan ended up being paid. This one was paid. This one was defaulted, paid, defaulted. And this is the model is predicting. So it predicts this model will be paid with 95% probability. Okay, and it actually was paid. And similarly, it predicted this one would be paid at 87% probability, and it actually was, and it said 36% being paid, and that actually defaulted. So you can see how the model is doing at 50% probability, okay? Sorry. This is with the threshold at 50%, okay? If we set the threshold of the default, this is greater than 50% probability, so that's true. 50%, that's also true. We make one mistake, okay? The model's predicting that it'll be paid with 55% probability, but it actually was defaulted. And so at a 50% threshold, we make that mistake. We get that one wrong. Everybody sees that? The model gets that one wrong. I mean, you could just see paid, 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 default, default, paid. There's one mistake. What's going to happen, though, is we can change the threshold. We can say, what if we require a 60% probability? Okay? Then if we do that, it changes the mistakes. So now we pick this one up. We say, don't call it paid unless you're like 60% probability that it'll be paid. And so this one is now default correctly. Okay, and we didn't make any additional mistakes on that one because these were all much higher than 60%. And if we dial it up to 90%, then we add these two mistakes as well. Does that kind of make sense? I'll come up with a better graphic if that one didn't work. It's hard to explain with graphics. Okay, what about regressions? So there's no classes, so it's not possible to count mistakes like true positive, false positive, true negative, false negative. You agree? You can't do it. Okay, so instead the predicted values are numeric, so the error is somehow the amount you're off by. So if the actual result was 200 and the model predicted 180, then the error is somehow 20. Right, it's a number. Okay, and so you talk about things like mean absolute error and mean squared error. So these are both a measure of the total error. You look at all the mistakes and how big the error is, and you add it up in a way that gives you a measure of the big error. The thing to keep in mind when you're talking about those metrics is that it's unbounded. You can have a model that has an error of 6 billion, okay, and that model might actually be fantastic. Okay, that's okay. The absolute value of the error is not as important as the relative value. You build it again, and instead of 6 billion, it's 1 million. That's a better model, okay, it has less error. So yeah, when comparing models, lower values are better. And you can also talk about something called the R-squared error, all right, which is a nicer metric for thinking about models on their own. It's actually comparing them to the mean. So it's a measure of how much better the model is than just taking the most common thing, all right, the mean. So less than 0 means it's doing worse. You'd be better off just averaging the results and saying, 70% of people have diabetes, so you do too, except that we're talking about regression here, that's okay. If it's exactly 0, then it's no better than just taking the average. And if it's 1, then the model fits the data perfectly. So this gives you a nice metric for regressions. If you get the R-squared higher or closer to 1, that model is doing something useful, okay? In the interest of time, I'm not going to show you an example of that. Okay. Oh, there is time series too. The thing to keep in mind about time series is that time series depends on the sequence of data. So I'm going to ignore that. Okay. The idea of time series is that this data is dependent linearly, so you can't do that random split like we did before. You'll get nonsense. You can't take the first 3 years and predict that year and the next 6 years and predict that year. You're trying to use all the years to predict the future. And so you do what we call a linear split instead. So you take this original training set, which is sorted by time, and your test set is going to be a holdout for the future, just like I did in the Oscars. You're going to hold out a part of the future, and then you're going to build a model and compare what it thinks about the future that you know about. So you're kind of pretending that 4 years ago was the future and seeing how you did then. Okay. Now we have to talk about ensembles, which I'll do in 2 minutes. Are you ready? I'm going to run over a little bit. I apologize to the next speaker. Okay, rather than build a single model, the idea is we're going to combine the output of several typically weaker models into a powerful ensemble. Okay, question number 1 is, why is this necessary? Question 2 is, how do we build weaker models? Why would you even do that? And how do you put them back together? What do you do with 100 models? How do you make the 100 models back into one? That's kind of tricky. Okay, so remember, and I'm going to go a little faster through this, because this is probably a little more detail than you actually need. But remember that no model is perfect, so any given machine learning algorithm just might not be able to do whatever it is the data set needs to model it. It just might not be possible. It's just too complicated, okay? Try to fit a line to a curve, all right? Even if the model is somehow super capable, has this high representational power, the real solution might just be elusive, okay? These models are sometimes what in computer science they call NP hard. It's just too difficult to even find the solution in a reasonable amount of time. And so you just kind of have to take the best solution you can find. And these practical algorithms, things that do these NP-hard problems in a reasonable amount of time, are using a lot of random processes, okay? Now you can prove that they're converging nicely, but they're still random. It's possible that there's a whole nother equally good or even slightly better solution if you just started with different initial conditions. And what's to say that model isn't the one you wanted? Okay, so you can take advantage of that by having both models. And if that wasn't bad enough, your data isn't perfect either. You're always working with the finite training data. Okay, remember the idea is you're taking 1,000 patients and trying to build a model that can predict for whether or not everybody in the world has diabetes. Right, so it's just like little dots in this giant matrix of possibilities. So every model is an approximation. Okay, so there could be several good approximations. There might not just be one. There could be 1,000 good approximations. You can also have anomalies. Okay, you have discrete training data, so there could be really unusual people in that data or not unusual people in that data. Those outliers can skew your model. You just have mistakes. You know, does the model have to do everything for you? I mean, come on. No, that's a joke. But really, there's always mistakes in your data. There just is. It seems to be unfortunate truth. So ensemble techniques. So the key idea is that by combining several good models, we might get closer to what the actual best model you could build is. Rather than just trying to spend all our energy building one great model, we're going to try to build 100 great models, or maybe 100 sort of great models. And then when we put them back together, we're going to get an even better one than we could have by just trying to build one. And we want some diversity. Okay, it's not useful to have 100 models that are all exactly the same. So we can do this lots of different ways. We can do it by doing tricks in the training data, you know, only show some data. We can do some randomness. We can do some funny weighting stuff. Okay, we can do some prediction tricks. And I'll show you a few things. So here's a very simple example. Here's a curve. Let's say I want to fit a line. Okay, that model is not complex enough, right? It doesn't fit that curve very well. So instead, I could say, let's just partition the data. And I'll train one model on that spot, one model there, one model there, one model there, and I'll glue those models together. You tell me where the input data is. I go to the equation of each one of those lines and tell you what the prediction is. And this is essentially an ensemble. It's not a very good one, but it's at least visually showing you how doing different parts of the modeling process in different models can give you a better result. Okay? So here's one way, called the decision forest. So the idea is you take your data set, and we're going to build trees just like before, but we're only going to use some of the data. So here's the whole original data. We're just going to show this tree a little bit of the data and let it build a model. And then we're going to show this other tree a little bit different data, and that one a little bit different data. And we're just going to build a whole bunch of trees, as many as you like, each one with just some of the data. They never see all of it. Which, if you want to think about it, allows each model to somehow specialize on a little segment of the data. Okay? But we do this in a very random and very controlled way in that sense. And then we're going to put the predictions back together at the end. You can also do something called a random decision forest. I mean, that other one was kind of random too, but this one's even more random. Same idea, we're building lots of trees on samples, but we're also taking some features out too. So every time you're building a tree, you take some of the features out too. You go, you know what, you're making predictions about homes, but you don't get to know about square footage. I'm taking that one away from you. So you got to build all your, it's not quite like that, I know, don't glare. It's actually making that decision at every split, but it's significant, or close enough. Okay, so we do this with different samples and different features, building lots of models and putting them back together, okay? You can also do something called boosting, where you're actually more concerned about the actual error of the model. So here's our home prices, we build a model, it makes some predictions, okay? We can compare the predictions, and we can just look at what the errors were. All right, this house price was off by 750, and this one was off by 625, that one's off by 12,000. Why don't we just build another model that predicts what the error is? Just take that error and glue it into this same data set, build another model. And then when you have your predicted error, you just glue them together. And you can think about this as like, hey, model one, what do you think the sale price of this home is? Okay, and then you're like, hey, model two, how much error do you think model one just made? Okay, and then you just add those two things together. So you're building a model to predict the error of the first model. Why can't you do that? That can work. But you do this again and again. Okay, you don't just do it once. So you build one model, and then you predict the error of that one, then you predict the error of the errors, and it's turtles all the way down. Okay? And the cool thing about this is that you can basically make this fit as tightly as you like, okay, which is also fraught with errors, so there's ways to avoid overfitting in this case. But this is the basic idea of boosting. You're basically modeling error at each iteration. Okay, let me show you an example of all those, which will be a little quick. Okay, so we'll take our same training set here. And out of the box, I'll just do what we call a one-click ensemble. Okay, this is going to do that first type of model I explained, which was by default, it's going to build 10 trees, okay? And it's going to use each tree is built with a sample of the data. Now, the tree visualization is gone. Actually, it isn't. It's hiding here. You could look at each tree if you wanted to. But what you get by default is that partial dependence plot. So you can see the decision boundaries. So notice how much more nuanced this is than a single tree. I can actually show you. Here's what this decision boundary looks like with a single tree. Okay? Or here's a different tree, for example. So these are the decision boundaries of each random trees selected from this ensemble. And when you put them all together, that's what it looks like. So you can see it's very nuanced in here. I remember before, or maybe you remember, we had this really blocky with the one tree, and now we have a lot more nuance in that decision boundary, okay? Super cool. Everything else, though, works the same, okay? You can make predictions now and everything else. Exactly the same, okay? Oh, I got to build more. So let's go back to the data set, and instead of doing a one-click, we'll go ahead and do a boosted. And we'll just let that run too. Boosted trees. Go forward and boosted, and we won't bother to wait for it. We'll just run it here. And I'll show you a random decision forest as well. So we'll go ahead and configure an ensemble. And this time, I'll show you some of the options that are available. So you can tell the number of models. You can go up to 1,000 if you like. So that's a parameter that you can control. If I do a decision forest, I can come down here, and in the tree, I can just click randomize, and that'll give me a random decision forest now as well. Okay, so if you're familiar with RDF, that's how you get one. So this will now give us another ensemble as well. So those three different kinds of ensembles I was showing you before are now built on this data set. Okay, and so with that, we can actually go ahead and evaluate all of these. Let's do it. So we'll take this one, we'll evaluate it. And which one did we do first? Bootstrap. We'll evaluate this one too. I should write a script to do this. Yeah, I'm just going back to the ensembles view where I have those three ensembles that I built, and we're just running an evaluation on each one. Okay. So now we have 4 evaluations, the one I did on the single tree and the 3 new ensembles. We'd kind of like to compare them all, right? We could look at each one individually, so we can actually see this one has quite a bit more accuracy than the single tree did. Okay, remember it was like 73 or something. But let's look at them all, so we can compare multiple evaluations. Okay, and this will actually show us that same kind of ROC curve, but for all 4 of these. So we here have the single tree, then the 3 ensembles. Okay, and I did not do a very good job of explaining what this curve is actually showing you, but in an overall sense, what you're looking for is the best model ever would be up here in this left-hand corner. Okay, that would be a perfect model. And so the closer you get to moving this decision boundary to a straight line here and a straight line there, the closer you are to a perfect model. And so what you're looking at when you compare this area under the curve is you're just looking at this decision boundary, or not decision boundary, sorry, this false positive, true positive rate boundary, and looking at the sum. Right? As you get closer, this area under the curve would be 1. So values that are closer to 1 are closer and closer to a perfect model. Okay, so it's just a nice way of ranking them overall. So we can see, for example, that this lowest one has an AUC of 0.80, and that one's an 8.2, and that one's an 8.3, and that one's an 8.37. Okay, so higher is generally better if you don't care about any other metric. Okay? That was very hand-wavy, I'm sorry. Okay. You could just keep going, though. I mean, there's lots of ways you can make ensembles. Here's another one. This is essentially an ensemble technique. You could actually build, you take your data set and build a model, an ensemble, and logistic regression, and then you could use those to make a new data set that has all those predicted values, and you could use a logistic regression to essentially predict which model you trust for any given data endpoint. So if you want to think about, one way to think about this is when you're predicting with this thing, you're going to predict with each of these, and then you're going to feed that back into this one as well. And the logistic regression is basically telling you, for that data, I'm going to say you go with the model. Or for that data, I'm going to say you go with the ensemble. So it's very meta. Okay, very modeling the model. So which one do you want to use? The one that works the best is the one you want to use. Okay? No, but seriously, did you evaluate, right? I mean, which one? Okay. So now that we got that joke out of the way, let me give you some really rough guidelines. Okay? But seriously, the one that works the best is usually the one you want. Okay, so for a really large, complex data set, you probably want to use a decision forest or a random decision forest with a deeper node threshold. Okay, you can allow these trees to get very deep, lots of splits, or you can have them be very short. Those are ways you can play with parameterizing the trees. Okay, and OptiML will actually do that for you. It'll tell you how many nodes you should use. But if you have really, really big data sets, this is a nice way to reduce the complexity of that. Even better is to use boosting with more iterations. Okay, but boosting takes much longer. All right, because you have to build each tree one at a time. Whereas in the decision forest, random decision forest, you can build, if you want 1,000 trees, you can build all 1,000 in parallel. Because they're all independent. So you can build 1,000 trees, you just crank them out. But boosting, you want 1,000 iterations, it's one, then the next, very serial. Okay, so for really noisy data that's got a lot of noise in it, boosting may overfit, and random decision forest is generally preferred. Okay, very hand-wavy. All right, but the basic idea here is that random decision forest is sort of dropping things out at such a high rate that it tends to drop out all the noise overall. That's essentially, whereas boosting is going to be worried about everything. For really wide data, so lots of features, okay, thousands of features, 10,000 features, you're probably looking at an RDF as well. Again, it's dropping features out, and so each one of those trees is going to be sort of allowed to specialize in different features, and that generally works out better, okay? For really easy data, very small, not very many rows, not very many features, a single tree is probably fine. It's probably fine. As a bonus, it also has the best interpretability, as we've seen. It's really easy to understand a single decision tree, right? Okay. For a classification with a large number of classes, so not true, false, but imagine a problem where you have 1,000 classes. Okay, it's hard to imagine, I know. But maybe you want to build a model that predicts, I don't know, what author somebody might like. There's thousands of possible authors, okay? Tens of thousands even. Then boosting is going to be really painful, all right? Because when you're doing classification with boosting, it actually has to build essentially a tree for every class. So if you have 10,000 classes and you're doing 1,000 iterations, you're basically building 10 million models, and you're doing it's horrible. So it can be really slow for very large classification problems, keep that in mind. And then for your general problem, decision forest or random decision forest is likely better than a single model or boosting, in general. For any data you pull off the shelf, probably true. And boosting is going to be slower. And yeah, so now we'll do the summary and we're done. Okay, so models have many shortcomings, right? The ability to fit, the fact that solving them is often NP hard. Your data also has shortcomings. You don't have enough of it, and it's full of outliers and mistakes. Yeah. Ensemble techniques can improve on single models, okay, using some kind of sampling like the decision tree, or adding randomness like random decision forest, or by modeling the error that you're making in some kind of a boosting technique, or by modeling the models with some kind of a stacking approach, all right, where you just allow each model to make its mistakes and use another model to pick out which one is doing the best. And then I gave you some guidelines, at least overall, for knowing which one might work best in a given situation. And I don't know if we'll show it, so I will do one more thing for you, which is I will show you that you can also not worry about parameterizing these if you don't want to. So when you're configuring an ensemble, okay, I can actually just click that right there, and it will now find the optimal, by which I don't mean BigML's optimal, but the optimal, M-A-L. But it'll now search the space of the ensembles for the optimum parameters. So the number of trees, the node depth, whether or not you want missing splits, it'll try them all and find it. Okay, so you don't have to parameterize these ensembles yourself. You can ask it to do it automatically. Okay? Okay, that's it.